Okay, so we're going to start with an example. And suppose in this example that we have a Hilbert space. And it's going to have dimension 2. And so the fact that it has dimension 2 means that if we write down a basis, it's going to get guaranteed to have 2 elements. And so I'm going to call the basis A and B. Okay, and now because it's a Hilbert space, that means it has an inner product. And so I'm going to tell you what the inner product is. And I'm going to tell you what the inner product is just by listing all the possible non-zero inner products. So the inner product of the basis element A with itself, I'm going to tell you is 2. And the inner product of B with itself, I'm going to tell you is 2. And I'm going to tell you the inner product of A with B, written in that form, is going to be 1 plus I. Remember, the inner product can be a complex number, but the inner product of something with itself, like here, has to be a real number. So those had to be real, but this is the inner product of 2 different things, so it can be complex. And in my example, I've chosen it to be true, that it's complex. Okay, then I don't have to tell you this, because it follows from what I already have told you, that if I take the inner product B with A, that has to be the complex conjugate of A with B. So that must be 1 minus I. I have no choice. If I told you it was anything different, then you would know I was lying. Okay, and now I've told you all the possible inner product pairs of A with B. And so you know what the inner product is for any vector in the Hilbert space by taking linear combinations. And we'll see how that works in just a second. Before I do that, I want to mention this is not an orthobasis. Okay, this is a basis, but not an orthobasis. If it were an orthobasis, then this number would have been 1, and that number had to be 1, and that number would have had to be 0, and that number would have also had to be 0. That's what makes it an orthobasis. That's what would have made it an orthobasis if it were 1. But no, this is just an ordinary basis. Okay, so let's define a vector V, which is going to be a linear combination of my basis vectors. So I'm going to choose it to be 5A plus 2 plus I times B. And I'm going to ask the question, what is its norm? Okay, so the first thing I want to do when I'm going to find the norm is I'm going to ask the question, what is the corresponding bra? Because for every ket, there's a bra and vice versa. And so what I'm asking is, what is this object? V with the angle brackets, with the left angle bracket, makes it a bra. And that's going to be 5 times A bra plus 2 minus I times B bra. Okay, and so the crucial thing here is that when you're finding the corresponding bra for a ket, I have to remember to take the complex conjugate. So that was the complex conjugate of this. 5, of course, is the complex conjugate of 5, so I didn't have to do anything there. Okay, so now I can compute the inner product of V with itself. And that's just going to be, I write the corresponding bra, 5A plus 2 minus I, B, acting on 5A plus 2 plus I, B. All right, now we just need to distribute everything out. And so there's a 5 times 5 makes 25 AA there's a 5 times a 2 plus I times A inner product with B plus 5 times 2 minus I inner product B with A plus, now I need to multiply my 2 minus I, 2 plus I, inner product B with B. So I just distributed everything out. This from the given information is 2, so was the BB. AB from the given information was 1 plus I, and BA inner product from the given information was 1 minus I. Okay, and so when you multiply that out, you get 50 plus the second number is 5 plus 15I. The third number is 5 minus 15I. And the last number is, oops, this BB. I don't know what I wrote that for. I meant to write 2. Okay, and the last number is 10. Okay, and so the whole thing is equal to 70. And as a sanity check, the inner product of anything with itself has to be real and positive. And so it's good that it was. Okay, so that's the inner product of V with itself. And so the norm, the thing to remember is to take the square root of V with itself. So that's the square root of 70. Okay, so just as a answer to what would be the unit norm corresponding to this, if I take the vector V and divide it by its norm, which in this case would be 5 over the square root of 70 times A plus 2 plus I times the square root of 70 times B, that's guaranteed to have unit norm. Okay. All right. So another thing we can do that's similar to what you do on the homework is let's find an orthobasis. Since AB wasn't an orthobasis, let's find one that is. And for that, the algorithm is Gram-Schmidt. There's more than one algorithm. For some specialized problems, it turns out Gram-Schmidt is not the most efficient thing, and there's more efficient things. But Gram-Schmidt sort of always works. And so it's just nice to have a recipe that we know is always going to work. Okay, so if you refer back to it, step 1 of Gram-Schmidt is to just choose any one of the basis vectors as your first one. And so we're going to choose A. Why not? We're going to choose psi1 is equal to A. And then if you look at step 1, the one thing you have to do with it is you have to make sure you have to renormalize it. And so what you do is you define the orthonormal version of it, which I'm calling phi, to be A divided by its norm, which was specified to be 2. The inner product was 2, and so this is just A over square root of 2. So that's our first orthonormal basis vector. And now we go to step 2. And so at each step, what you do is you choose another one of your vectors. So this time, the only thing left is B. We'll choose that. On one of the homeworks, you have a dimension 3 one, so you have a choice, but you should just choose them in the order given, I think is the easiest thing. Okay, and so then we define this thing psi2 tilde, and psi2 tilde is psi2. And what you do is you subtract off the projection onto every previous vector. So in this case, it's phi1, phi1, psi2. Okay, which in this case is going to be B minus a over square root of 2, a over square root of 2 times b. Okay, so that's b minus 1/2 a. And then a inner product with b was 1 plus I. And so just to rewrite this in a prettier way, this is minus 1 plus I over 2 times a. Okay, now to complete step 2, what we have to do is take the, oops, I forgot. That's plus b. That wasn't done there. Okay, so as a reminder, the final thing you have to do in each step is to make sure that your ortho basis vector indeed is norm 1. And so we need to define phi2 to be psi tilde 2 divided by its norm. Okay, and so we need psi2 tilde, psi2 tilde, which is equal to the inner product of b minus 1 minus I over 2a, inner product with b ket plus 1 plus I over 2a. Okay, and once again, I want to remind you that what we had to remember to do here, this is a common thing to forget, we had to take the complex conjugate when we formed the bra corresponding to psi tilde 2. Okay, so now you can multiply that all out. I won't go through all the arithmetic. It turns out that when you multiply all this out, you get the number 1, which was totally lucky. Normally, it won't work out that way. But in this case, it just so happened that the inner product of psi tilde 2 with psi tilde 2 actually was, it already had unit norm. Okay, and so phi2 is equal to minus 1 plus I over 2 a plus b. If it hadn't had unit norm, we would have taken the square root of this quantity, whatever it happened to be, and divide by it in order to get our phi2. Okay, so we're now done because we only had dimension 2 in this example. If we had step 3, we would have had to choose a new vector, subtract off its projections onto all previous vectors, take that thing, renormalize it by dividing by its norm to get something with unit norm, and continue until we were done. In this example, oops, I'm going to go back to this. So we want to do checks. So check are that phi1 inner product phi1 is 1. Phi2 inner product phi2 is 1. That's really the thing right up here where I said lucky. And phi1 inner product phi2 is 0. And phi2 inner product phi1 is 0. And so all of those things put together are telling us that we indeed have an orthobasis. Okay, questions on that? So I think that you'll find that to be similar to at least one of the homework problems. And that illustrates the idea of how to do a Gram-Schmidt. No questions? Somebody shout so I know you're still there.
Hi.
All right, very good. I think I'll turn off my video to save bandwidth. All right, so then last time we had started talking about operators. And just as a note of notation, in this class, I will almost always, in fact, I can't think of a counterexample, use capital letters. Not all books do that, but that's going to be our convention, as we'll try, unless there's some good reason not to use capital letters. And so a generic operator might be A, capital A. For position, we'll use X. For momentum, P. Later on, we'll talk about angular momentum, which is L. So this A would be something generic. When I can't think of anything else to call it, I'll call it A. This would be position. P would be momentum. I don't know why momentum is P, it's just, that's tradition. L would be angular momentum. But some books will use lowercase letters. Some books will put a hat on the thing to tell you that it's an operator, but I won't. So some books put hats on operators. So they would write A hat, for example, or X hat or P hat. But to me, it's not worth it because it sort of clutters everything up to put all the hats everywhere. Some books will use bold-faced, but bold-faced is really hard to do in a spontaneous lecture. Okay, in any case, if I've got an operator, what it does, it acts on a vector or a ket to give you back another ket. So we might decide to call that other ket V prime. It also can act on a bra from the right. So if it does, that's a bra, which I can write as, let's say, V double prime. And so one thing I want to emphasize at this point is that the corresponding ket for V double prime may or may not be V prime. And in the next lecture, I think, is when we'll actually say under what circumstances it is and what circumstances it is not. Okay, so some examples. The first example we talked about was the identity operator, which we call capital I. So capital I acting on any vector is equal to the same vector back for every vector or every ket. Okay, another example of an operator is this. Yes, go ahead.
Excuse me, Professor. In the bra one, the V, and then there's a line, there's an A, and then there's a line after A.
Oh, very good. That should not be there.
Oh, okay.
I don't know why that snuck in accidentally. Very good. All right. So so another example of an operator that you can form is something like this. I can take a ket and then put it next to a bra on its right of any two vectors V and W. So this is an operator. It looks like a ket followed by a bra, and it is, but it's also an operator. And why is it an operator? It's because if I act on a third vector, let's just write down what that is. That's V, and then W inner product X. And W inner product X is an inner product, so it's a complex number. So that's just saying, what ket is A acting on X? It's proportional to V, and that constant of proportionality is this number W inner product X. So that's an operator. Not every operator can be written in this form. Some can, some can't. So not every operator can be written as a ket followed by a bra. Okay, and at the end of last time, we talked about one example that can be written that way, and that's the projection operator.
Professor, could you,
Yeah.
could you please also set an example of an operator that cannot be written?
So one example of that would be the identity operator. And we'll get to that. We'll get to why exactly that's true in a second.
Okay, thank you.
Okay, good. But most operators, I don't know what I mean by most, but many, many operators cannot be written in this way. It's very special operators that can. All right, so the projection operator onto a given vector, let's call it x, and we'll just assume that it has unit norm. If it doesn't, you can divide by its norm to make it have unit norm. That would be p sub x is x, x. So that's an example of an operator that can be written in the ket bra form. And so how do we know what this thing is? We act on any v, let's say, and the answer we get back is proportional to x. Namely, it's x times the number x inner product v. So this is a ket proportional to x. Right, so given a ket x, you can make a projection operator out of it. Okay, so note that if I act with p sub x on this very same vector that was used to define it, I just always get back x. So I project onto x, I get x. Okay, and if I project onto anything orthogonal to x, let's call it v, I'm going to get 0, or the null ket, if they're orthogonal. And so that's the sense in which it's a projection operator. It's basically throwing away everything that is perpendicular or orthogonal to x and keeping everything that's in the same direction as x. Okay, so recall that if you're given an ortho basis, so recall that for an ortho basis, that's a set of kets phi, which are labeled by some index j. J is going from 1 up to the dimension of the Hilbert space. Let's call that n. Recall that you can write v, any vector, as, first of all, it's the identity operator acting on v, but it's also the sum from j equals 1 to n of phi j, v. That was something we derived last time. And now we recognize that what is this? This is just, each one of those things in the sum is just a projection operator. We can call it, I could call it p phi sub j, but let me just call it p sub j to be a little bit shorter. Okay, and this is true for every v. And so now by comparing the equal signs, what we learn is that we can write the identity operator as the sum from j equals 1 to n, phi sub j, phi sub j. So this is an extremely useful thing. This is known as the completeness relation. Okay, and what it says is, if you're given an ortho basis, then here is a neat way of writing the identity operator in terms of the ortho basis. You sum over from 1 to n of the ket and the bra for each ortho basis element, and that's guaranteed to be the identity operator, which I could write also just like this, j equals 1 to n of p sub j. So to answer your earlier question, this is an example of something that is not just a operator of the ket-bra form, but it's a sum of operators of the ket-bra form. You can't just include one of them in this completeness relation. You have to include them all when you sum over them. So as I said, I can't emphasize enough that this is going to be extremely useful. I should highlight it because it's almost going to be a joke that when we don't know what else to do and we're stuck on something, try the completeness relation. It will probably help. And it certainly won't hurt. Okay. So another thing about the projection operators for an ortho basis is also, let's say I take two projection operators and I multiply them together. So what does this mean? This means first I act with P sub k, then I act with P sub j. This is equal to phi j, phi j, phi k, phi k. But because it's an ortho basis, that's equal to the Kronecker delta. That's what an ortho basis means. And so I didn't leave myself enough room there, but that means Pj, Pk is equal to delta jk. So it's 0 unless j and k are the same thing. And if they are the same thing, then I only need the P sub k projection operator. I don't need them both. Okay. Any questions on that? Okay, let's do another example of another operator thing. Another way to define an operator. So in this case, you can say, suppose your, oops, I don't know why that happened. Suppose your space, you can call it a state space or a Hilbert space, has an orthonormal basis that I'm going to call 1, 2, and 3. The 1, 2, and 3 are just labels for the different orthobasis elements. They may or may not correspond to any physical quantities. So I can specify an operator by telling you how the operator acts on each one of the orthobasis elements. So let's call my operator R sub alpha. And it's going to be defined by just telling you what it does. So R sub alpha acting on 1 is going to be cosine alpha times 1 plus sine alpha times 2. Okay, so R sub alpha depends on what alpha is. It's really a whole family of operators. If I tell you what alpha is, then you can construct this thing. R sub alpha on the orthobasis element 2 is going to be minus sine alpha 1 plus cosine alpha 2. And let me say that R sub alpha acting on 3 is just the ket 3 back again. Okay, so if I've told you all those things, then I've told you everything there is to know about R sub alpha. Okay, so since the action on the basis is specified, the operator is fully determined. And so in principle, you know everything there is to know about it. It's fully determined acting on any ket, because any ket is just a linear combination of 1, 2, and 3 kets. But it's also true that it's fully determined acting on any bra. And we'll see that exactly how that works in a little bit. Or maybe next time. Okay, so Yet another way to specify what an operator is in terms of its matrix representation. So let's explain what that is. So this is the matrix representation. I think from now on, I'll probably write rep instead of representation of an operator. Just for variety, let's call this operator omega, capital Omega. In a basis, let's call my basis for variety psi sub j. And I'm not actually saying it's an orthobasis necessarily, may or may not be. Okay, then omega acting on V is equal to omega acting on, a different way of writing it would be in terms of its components. V sub j, psi sub j, right? So the V sub j's are the components of the vector V. And the thing about operators is they just move right past ordinary numbers. V sub j's are just ordinary numbers. And so I can write this equally well as sum over j, V sub j, A acting on psi sub j. Okay, and now what I can do is I can write psi sub k bra acting on what I've just written.
Excuse me, sorry. Instead of A, shouldn't it be omega? Isn't that what we're calling the operator?
Very good. Sorry. Oops. I'm switching notations in my mind without, I did it here too, didn't I? Oops. Okay, so psi sub k omega v would be sum over j of my components, v sub j, and then psi sub k omega psi sub j. Okay, so what I've done is I've written everything there is to know about how omega acts on v in terms of the components v sub j and then these numbers. These numbers are n squared because j runs from 1 to n and k runs from 1 to n, complex numbers for j and k independently being from 1 to n. Okay, and these are known as the matrix elements of my operator omega in this basis. Okay, and I can write that as omega subscript k subscript j. All right. So now let's consider the case where it's an orthonormal basis. So that's just a specialization of this. Okay, if V prime is equal to omega acting on V, then, and so since it's an ortho basis, I'm going to call them phi's instead of psi's. Phi sub k acting on V prime. Those are the components of V prime, which I'm calling V prime sub k. They're equal to the sum from j, well, j to 1 to n, I won't write that, of phi sub k omega phi sub j times the components v sub j. Okay, so these are the components of v. The vk primes are the components of v prime, which was omega times v. And so what I can do is make this look a little nicer by writing it as one big matrix equation. And what I do is I take the V primes and I turn them into a column vector. So V1 prime, V2 prime, up to V sub n prime. I write this as a big matrix, which looks like phi1 omega phi1, phi1 omega phi2. These are the matrix elements, phi1 a phi n. Oops. Okay, and then the next row of the matrix is phi2 omega. I did A again. Okay, phi2 omega phi1. And this is going to be phi2 omega phi n. And then the last row of the matrix is going to be phi n. Oops. Omega phi 1. And this is going to be phi n omega phi n. All acting on V1, V2, up to Vn. Okay, so this big matrix equation that I've written has the same form as what I wrote up here in terms of the operators. So the way to think of this is the operators are abstract. But in any given basis, they are just matrices. Technically, we should say they're represented by matrices in a given basis. But you might as well just say that they are matrices, because effectively that's what's true. Okay, so in any given basis, the operators become matrices. But if I choose a different basis, which we will do later, then they will be different matrices, even though it might be the same operator. Okay, now we can do products of operators. Okay, let me go back to A and B. So if I have A times B, this is defined. I already actually did this for projection by operators. So if I have A times B acting on a ket V, that's equal to A acting on B acting on the ket V for all V. So if I do that, then it's a nice fact that the matrix for AB just obeys matrix multiplication. In other words, if I take A times B in an ortho basis and ask what is its matrix elements, what are its matrix elements, Kj, that's equal to the sum over M of AKM times BMJ. So this is matrix multiplication. Okay, so operators obey the same rules as matrices within any given orthobasis. All right, so what else can we do with operators? We can discuss the inverse of an operator. For variety, let me go back to omega. And so that's just defined by saying omega inverse acting on omega is the same thing as omega acting on omega inverse has to be the identity operator. So an important thing about inverses of operators is they often do not exist. So omega inverse may not exist. And so one thing we will often want to know is, does it exist or does it not? It's a question that has to be answered. First, let me give an example of where it doesn't exist. So example of a non-invertible operator is, let's say I have a projection operator onto some state X. Or some ket X. So notice I'm not summing over the X's. This is just one single X. And so the reason heuristically why this thing can't have an inverse is because if I act with this on some other vector v that happens to be orthogonal to X, I'm just going to get 0. And then the inverse would have to somehow resurrect the original state that I had. But there's no way to start with the null ket and act with any operator and get anything other than the null ket back. Right? So this thing is just this thing is never going to have an inverse. Projection operators don't have inverses. Now the identity was the sum of a bunch of projection operators, and so that does have an inverse, but a single projection operator does not. So more generally, a way to look and see whether a operator has an inverse is the fact that, let's say I take the matrix for an inverse operator, assuming for the moment that it does exist. Okay, so what does this mean? This means operator inverse that should be equal to, and you can prove it using the matrix multiplication trick that we discussed a minute ago. This is equal to the matrix for the operator omega inverse. So this means the matrix inverse, just from linear algebra. Okay, so then what we can say is the operator omega inverse exists if and only if the determinant of the matrix for the operator is non-zero. Okay, so if you're given an operator, you can find its matrix elements. That amounts to basically going up here. That's your matrix for the operator, is you look in the orthobasis and you take all of its matrix elements. The matrix elements are the individual parts, like that one or that one or that one. Right? And so if your matrix for the operator has a determinant that's non-zero, then you can construct its inverse, and then you can construct the inverse for the operator by sort of undoing it. Okay, another thing that we can do with operators is form their commutator.
I'm sorry, Professor.
Yes, go ahead.
Forgive me, my background in math isn't too strong. So that omega inverse, so you have matrix for omega inverse equals matrix for omega, all of that inverse. What's the difference between these two?
So on the right, you're saying you take omega and you first make its matrix. Then you invert that. And on the left, you're saying first you take the operator and you form its inverse as an operator, and then you make the matrix out of that. And as to what's the difference, that's what the equality is telling you. The equality is telling you that, fortunately, there is no difference. They are the same thing.
Can you repeat what's the first side one more time?
What the left side or the right side?
The left side, the left side.
So the left side is first you take the operator's the operator inverse as an operator, not as a matrix, just as an abstract operator. Then once you've formed that, you take its matrix, and that's guaranteed to be it if you did the same thing as if you did it in the opposite order. If
So
you
what
first,
exactly, I'm sorry, what exactly is the operator inverse?
so that's defined by this statement. The inverse of an operator is the operator such that when you multiply by the operator, you get the identity in either order. So it's sort of an abstract definition, right? This doesn't come with a recipe telling you how to construct omega inverse, but that's okay because that's actually what this is doing right here. This is telling you how to construct the operator. You can do it by first turning it into a matrix, taking the inverse of the matrix, and then turning that back into an operator. So really the takeaway though, is that the answer to your original question of what's the difference, there is no difference.
Could you please set an example of an operator inverse?
Yeah, we probably should do that, I think, next time. But the only operators that we have so far that have nice inverses are the identity, but the inverse of the identity is the identity, so it's kind of boring. And then we have the projection operators, but they don't have inverses, so I can't give you that either. But I'll do an example next time, I promise.
Thank you.
Okay. All right, so we have the commutator of operators. Since we know how to multiply operators, the commutator of, let's say, A with B, which we always use square brackets for, is just defined to be A times B minus B times A. In a orthonormal basis, we can write this in matrix form, right? So we can write that the matrix for the commutator AB is equal to the matrix for A times the matrix for B in the usual matrix multiplication minus the other way around. And so if you're asking what's the difference, again, what this is telling you is that fortunately for us, there really isn't any difference. You can think of operators as being represented by matrices in a very straightforward way so that you can do the operations that you want using matrix multiplication. And that will correspond exactly to what what you would get from doing it in operator language first, and then turning that into a matrix. So going back to this matrix representation of our operator omega, okay, a lot of times that's going to be the easiest way to deal with an operator. Turn it into this big matrix, do what you need to do with it, find its inverse, for example. Later we'll talk about finding its eigenvalues, doing other operations, and then that matrix representation is, for all intents and purposes, the same thing as the operation done directly in terms of operators. So in this case, let me just be more specific here. If I take the commutator of A and B in an ortho basis and ask for its matrix elements, J and K, that's the same thing as the sum over M. Each of these indices is labeling an ortho basis element of AJM, BMK, minus BJM, AMK. So it's exactly the same thing. That's the standard formula for matrix multiplication. All right, so we're out of time for today. The next operation we're going to talk about for next time is going to be adjoints vectors and operators. All right, so that's it for today. And I believe you do have homework due on Wednesday. So if you have questions, be sure to let me know. And otherwise, I'll see you on Wednesday.
Thank you.
Sure.
Yeah, thanks. Have a good day, everyone. Bye.
Thank you.
Bye.
Good one.
Bye.
Good.